In today's class, we would be looking at the energies of orbitals, right, or energies of subshells, SPDF, right, that we have been doing for a long time now. So energies of, we would be talking the energies of orbitals in two references. First is the energies of subshells of single electron atom like hydrogen, and then we will see the energies of subshells of multi-electron atoms, right? Multi-electron atoms those that contains more than one electron like lithium, right? So for hydrogen atom, the energies of its subshells, right? Energies of its subshells of various shells is same, right? Energies, basically what we are saying is that the energies of subshells is same, right, for a single electron atom like hydrogen, whereas energies of subshells of multi-electron atom is different, right? So what is the cause of this difference in the energies of subshells of multi-electron atom? This we would be looking at. First, let's quickly understand the energies of, let's quickly first draw the diagram, energy level diagram for hydrogen atom, right? For hydrogen atom, this is how we will draw the energy level diagram. This is 1s, this is 2s, right? Then you have 3s, 3p, 3d, right? 3s, 3p, 3d, right? These dashes represents the orientation of these shells, that is the orbitals, right? So here you will notice that these orbitals, right, these orbitals like 3s, 3p, 3d and this 2s and 2p, all these are at same energy level, right? Similarly, 3s, 3p, 3d is at same energy level, right? Now, if I draw, this is for single electron atom like hydrogen atom, right? Now, if I take a if I draw the the energy level diagram for a multi-electron atom, the energies will look like this. This is 1s, this is your 2s, right? Now, the energy of these two orbitals or subshells in case of multi-electron atom would not be same, right? It would be like this. Energy of 2s or s orbital is less than, now this is 2p subshell, right, of the same shell, second shell, but in the diagram I'm showing it above 2s. That means the energy of 2p is more than 2s, right? Similarly, if we talk about this 3s, the third shell, the energies of orbital or subshells would be different. That is, the energies of subshells SPD of third shell would be different, right? And this is how it will look like, right? So this is 3s, 3p, 3d. That means energy of 3s is lowest, 3p is above that, and 3d is highest. The energy of 3d is highest. So from this, or for any atom, for any multi-electron atom, the sequence, the energy order is SPD, right? This is the energy order. The energy of S is lowest, then comes P, then comes D, right? Now we will look at the reason for these differences in energy, right? And for this, it's 1s, right? Then if I write this, 2s is equals to 2p, then you have 3s is equals to 3p is equals to 3d, right? Here I have shown this 2s is equals to 2p. That means energies of subshells of second shell right, is same, is equal. Energy of S and P subshell of your second shell is equal. Similarly, energies of 3 subshells SPD of the third shell is same, right? And these shells or orbitals, right, that have same energy, these are known as degenerate orbitals, right? These are degenerate orbitals. Degenerate orbitals, that means they have orbitals of same energy. These are degenerate orbitals, right? Now this is not the case with this multi-electron atom, right? This is your multi-electron atom. Now we will look into the reason for this difference, right? First we will look at one thing that we already know. We have discussed this in previous lecture. If this is the nucleus, right, say this is the, let's take example of lithium 1s2 2s1. This is the electronic configuration of lithium. Its atomic number is 3, right? So positive charge here would be 3 protons, right? It would be plus 3 positive charge due to 3 protons, right? And then you have this 1s2, right? Then you have the second shell, you have only one subshell S, like this, right? If you normally draw it, its electronic configuration would be, if you do the orbit diagram, 2 1, 2 electrons in the first shell, 1 electron in the second shell, right? To this electron, we call these electrons as core electrons, right? Electrons that are in the lower shells, that are in the inner shells, right? The electrons that are in the completely filled shells are core electrons, whereas this electron is your valence electron, right? Core electron and valence electrons. Now let's look at the forces that are acting on these electrons, right? In case of hydrogen atom, if this is your hydrogen atom, right, we have only one shell and this is your nucleus, so plus 1 charge, right? And this is negative electron that is revolving around the nucleus. So the force of attraction is only between, there is only one force that is working here between nucleus and the electron, right? So force is only between nucleus and electron, right? Now let's look at the forces that are working in case of lithium, right? We have the attractive force between nucleus and these core electrons, and then we have attractive force between nucleus and the valence electrons, right? Since these are oppositely charged, nucleus and electrons, so we have attractive interactions. Now what is the interaction of these core electrons with the valence electrons, right? We have the repulsive interactions between the electrons of the first shell and the outermost shell, right? And it is due to these repulsion, it is due to these repulsive forces that the energy is different, right, for multi-electron atoms, right? And what this electron is basically doing, right? Because there is an attraction between outer electron and the nucleus, right? And there is a repulsion between electrons in the first shell and electron in the outermost shell, right? There is repulsion. Now due to this repulsion, the effective force due to positive charge on the nucleus, right? The effective force on the electrons, the effective force on the outermost electron due to positive charge on the nucleus decreases, right? I'll just mention again, the effective force on the outermost electron due to repulsion due to these core electrons, right, will decrease. The attraction, this the force of attraction between outermost electron and the nucleus, right, will decrease, right, due to repulsion between the electrons, due to the repulsion between the electrons between the first shell and the outermost shell, right. This is known as screening effect, right, or shielding of outer electrons by the inner electrons. Inner electrons are applying repulsive force, right, and due to this repulsive force, the force, right, a force of attraction between outer electron and nucleus is decreasing, right. So the force that is getting applied on the outer electron is less, right, is not due to this +3 positive charge, right, but this force is getting reduced, right. So the effective attraction by the nucleus, right, is known as effective nuclear charge, right. Effective nuclear charge is getting decreased, right, for attraction on these outermost electron. Since the effective nuclear charge is decreasing, right, due to repulsion between these electrons, we call it as effective nuclear charge, right, and this is getting reduced due to the repulsion, and this is known as shielding or screening of outer electrons due to these inner electrons, right. This is the concept that we would be using, right, to explain this. Now let's look at these SPD subshells, right. Now so what we have noticed is, in case of hydrogen, right, within a given principal quantum number, right, the energy of orbital increases in case of multi-electron atom in this order, right. Now if you look at the hydrogen atom, the diagram here, I've just mentioned there that the force is only between nucleus and the electron, right. That means there is only one force of attraction. The only electrical interaction present in hydrogen atom is the attraction between negatively charged electron and the positively charged nucleus, right. Whereas in multi-electron atom like lithium, right, besides the presence of attraction between electron and the nucleus, we have the attraction between electron and the nucleus, right. So in addition to this attraction between electron and the nucleus, there are repulsion terms between every electron and other electron. There is repulsion between these electrons, right. Thus but we see that repulsive forces may destabilize the atom, right, but we know that the atoms are, this atom like lithium atom is stable, right. Why? Because the total attractive force between nucleus and the outer electron is more, right, as compared to the repulsive forces, right. That is why the atom is stable, right. So the repulsive interaction in explaining, right, this sequence, right, of energy, S is less than P then less than D, right, the repulsive interaction of electrons in the outer shell with the electrons in the inner shell, right, like I have explained, is important. It is due to this repulsive forces that the energy difference comes between these subshells, right. The attractive interaction of electron increases with the increase of positive charge. If you keep on increasing the positive charge, right, for example, if I take some other atom, right, that has higher positive charge in the nucleus, then the attractive force on the outermost electron will increase, right. But there is screening also. You need to consider the screening part also. There is screening or shielding of outer electrons due to these inner electrons, right. So the effect will be lowered due to, and this attractive interaction, right, this attractive interaction will be lowered due to repulsion or due to the screening or shielding effect of outer electrons that is caused by these inner electrons, right? So this effective force will decrease due to the repulsion between the electrons, or due to the screening of the positive charge, right, of the nucleus. So the effect will be lowered due to the effect. The effect means the attraction will be lowered due to the partial screening of positive charge on the nucleus by the inner shell electrons. These inner shell electrons, what they are doing is they are actually acting like a screen between the outermost electron and the nucleus, right? So they are reducing that attractive force, right? So this effect is known as the shielding of outer electrons from the nucleus by the inner electrons, right? This is very important. This is your shielding of outer electrons, by inner electrons, right? This is shielding of outer electrons by the inner electrons. This is important. This is known as shielding effect. Shielding of outer electrons, and shielding of outer electrons from the nucleus, right? This shielding is getting done. Let's try shielding of outer electrons from the nucleus, right, by the inner electrons. It is due to this primarily that the energy splitting takes place, or that there is a difference in energy of subshells, right? So both the attractive and repulsive interactions depend upon the shell and shape of the orbital, right? Both the attractive and repulsive interactions depend on the shape of the orbitals, right? Size and shape of the orbitals. Like s orbitals, right? We have to look into the s orbital interaction with the nucleus, p orbital, d orbital. Depending on that only this will take place, right? Both the attractive and repulsive interactions depend upon the shell and the shape of the orbital. Shell of the orbital means, one thing we know, that as we keep moving away from the nucleus, what we are doing is we are going against the attractive force. So when you go against the attractive force, you have to apply more energy, right? So as you keep moving away towards the outermost shells, towards the outer shell, the energy of the electron will keep on increasing, right? So energy of the outer shell would be highest, right? And the energy of the lowest shell would be minimum, because it is closest to the nucleus and there is high attraction between the between the inner shell and the nucleus, right? So it depends on these interactions depends on the shell and shape of the orbitals, right? Whether it is s, p, d, f, right? On these things it depends, because we know that s orbitals are spherically shaped, right? These orbitals, the s orbitals are, we know these are spherical in shape, right? Like this, right? They are spherical in shape and they are closest to the nucleus, right? The electrons in s orbital is closest to the nucleus. They spend more time close to the nucleus, right? So the attraction between the electrons that are present in this s orbital and the nucleus, this positive nucleus, this is your s orbital, this is your positive nucleus, and the electrons in the s orbital spends more time close to the nucleus. So here the attractive force is maximum. So when the attractive force is maximum, the energy of s orbitals is minimum, right? Because it's more stable, because the force of attraction is more. So the electrons in the s orbitals are stable, right? Similarly, if you compare it with the p orbital, the electrons that are in the p orbital will shield the outer electron from the nucleus more than the electrons present in the d orbitals, right? Why? Because we know that s orbital shields the outer electron from the nucleus more effectively. Why? If you look at this, since this s orbital is close to the nucleus, right, like I said, so this s orbital, the electrons that are present in the s orbital will shield the outermost electron maximum, right, from the nucleus. The effect of the shielding effect of electrons in the s orbital is maximum because it is closest to the nucleus, right? And so s orbital, the energy of s orbital is minimum, right? So let's look at the, and if you look at the shape of p orbital, it looks like this, right? The electrons that are present in the p orbital, right, they spend their time, they spend more time in the vicinity of nucleus, right? That is, they are not as close to the nucleus. The electrons in the p orbital, they are not as close to the nucleus as s electrons, right? So they spend most of the time, the electrons in the p orbital will spend most of the time in the vicinity of the nucleus, right? They are somewhere near the nucleus, right? And the electrons in the s orbital, they are closest to the nucleus. So the force of attraction between electrons in the p orbital and the nucleus is less, right, compared to the attraction between s orbital and your nucleus, right? So energy of p orbital would be higher, right, would be higher than the s orbital, because the electron in the s orbital are not as close to the nucleus as electrons in the s orbital, right? So, and if you compare with the d orbital, this d orbital, the electrons in the d orbital are more far from the nucleus, right? They are more far from the nucleus. So their energy, and the more you are away from the nucleus, the more is the energy, right? Like the more the shell is away from the nucleus, right? If the like we talk about the outermost shell is away from the nucleus, so its energy is maximum. Similarly, the electrons in the d orbital and in the p orbital is away from the nucleus compared to the s orbital, right? So since the electrons are moving away from the nucleus, so their energy increases, right? The energy of p is greater, the energy of p is less than d, right? And the energy of s, the electrons in the s orbital, their energy is minimum because they are closest to the nucleus. So this is the order, spd, right? Now since we said that the electrons in the s orbital, right, they are close to the nucleus, so when the electrons in the s orbital, right, will shield the electrons, the outer electrons, since they are close to the nucleus, so the shielding power of s electrons is maximum, right? The shielding power of s electrons is maximum compared to the compared to the p, then compared to the d, right? Shielding power of p is less than d and the shielding power of d is less than p, right? This is how it goes, right? You just have to remember one thing: the more electrons are close to the nucleus, more is their interaction with their nucleus, since this shielding is nothing but the interaction with the nucleus, right? So s electrons are close to the nucleus, so that is the reason they exert the maximum shielding effect on the nucleus, right, on the nucleus for the outer electrons, right? So the energy of s orbital will be lower than that of p orbital, which will have less energy than the d orbital, right, like we have discussed already. Since the we know that we have already discussed that the extent of shielding from the nucleus is different for electrons in different orbitals, right? So since the extent of shielding is different for electrons in different orbitals, right? So that is why since the energy we have seen is different, right? Energy is in this order, and the shielding effect is also different. That is why there is splitting of energy between S and P, SP and D, right? This is the reason there occurs a splitting of energy, right? So since the extent of shielding is different for electrons in different orbitals, it leads to splitting of energy levels within the same shell, right? That is what we want to explain, that why the energy of subshells is same in single electron atom, but this is not same in multi-electron atoms. Multi-electron atom, the energy, there would be energy splitting, or what we say is the energy for subshells, energy of different subshells is different in case of multi-electron atom, right? This is due to, now we have understood that this is due to the shielding effect of electrons, right? Shielding effect of inner electrons, right? What they do is these inner electrons act as a screen or a shield, right, between outer electrons and the nucleus, right? And they reduce the effective force of attraction between outer electrons and the nucleus, right? And if we talk about the electrons that are in inner shells, electrons in the inner shells, these electrons are present in s, p, d, different orbitals, right? Now we have understood that the electrons that are in s orbital, since these are different orientations, s, p, d, these are different orientations in three-dimensional space, right? So some are close to nucleus than others, some orbitals are close to nucleus than others, right? So s, the more close you are to the nucleus, the less is the energy, right? As you keep moving away from the nucleus, the energy will increase. So s is closest to the nucleus, right? And this shielding effect is nothing but the effect on the nucleus. Since they are closest to the nucleus, so their energy is minimum, and if for this, since they are closest, right, so their energy would be minimum. Energy would be minimum, right, because of high attraction, right, because of high attraction between electrons and the nucleus, but their screening effect, the screening or shielding effect would be maximum, right, because they are close to the nucleus. So they will screen the outer electrons, or they will shield the nucleus maximum, right, compared to P and D, right? So that is why there is splitting of energy, right? And why is there no splitting of energy in case of hydrogen atom? Because in case of hydrogen atom, there are no electrons, right, to screen or shield the nucleus, right, from the outermost electrons. Since there are no inner electrons that could exert the shielding or screening effect, so there is no splitting of energy in hydrogen and hydrogen like atoms, right? So I hope this is clear. And one thing, we have this energy, the energy of these orbitals can be seen from n plus L rule, right? If the value of n plus 1 is low, right, then the energy of the orbital is low, right? And one more thing, important thing, that in case of multi-electron atoms, the energies, right, the energy of these orbitals, energy of these subshells depend on azimuthal quantum number also. And in case of single electron atom, this energy of the orbitals depend only on the principal quantum number, right? So, and we have seen that these orbitals are nothing but azimuthal quantum number, right? These SPD orbitals are given by azimuthal quantum number, and we don't have these, and it is these orbitals that is causing the screening effect, due to which we have the splitting of energy. So n plus L rule is important, right? So the lower the value of n plus L for an orbital, the lower is its energy, right? If you look at this, L is equals to 0 for s orbital, right? So 1 plus 0 is equals to 1. For this it's 2. For P it's 2. So 1 plus 1 is equals to 2, right? And we know that P orbital has higher energy, and s orbital has lower energy, right? So less is the value